to the final. Okay. So I present to you chapter 9, 1 and 2 sample estimation problem. Okay. I'm gonna walk you through this some terminologies in estimation. Then we're gonna learn how to estimate a single mean. When I talk about single mean, it means one population or one group is involved. Then I'm also going to walk you through how we construct confidence interval. Confidence interval for single mean when population variance is known and when population variance is unknown. Okay, now I want us to get started. I want to first start by giving you some kind of definition that we need in this particular topic. Actually, I'm going to start with parameter. I'm not going to start with this. Let me first give you what do we mean by parameter. Okay, so what we mean, I want to first start from parameter. I think what I'm going to do is to define parameter, and not only that, to talk about sample. Okay, to talk about sample, and not only that, also to talk about population. Okay, talk about population, and after talking about population, then I'm now going to talk about statistic. Then from there, I'm going to talk about what to make an estimate or to be unbiased. But what I want to do right now, I first want to explain the connection between all of these. So I need you to pay attention. Let's say, for instance, I want to figure out the true value of a parameter. Maybe I want to know what is the average income in a particular average household income in a particular country, or maybe I want to figure out the numbers of citizens that actually get vaccinated. Okay, because I want to believe it's not going to be everyone that will be vaccinated. If I want to, if I'm interested in that, so actually, what I'm interested in is what we call parameter. Parameter is a population characteristic value that we seek to determine. Okay, that's what we call parameter. So if I want to get the average household income in a particular country, that's a parameter, which is going to be mean. If I want to get the number of people that get vaccinated in a particular district or county or country, that's a proportion, that's a parameter. So a parameter could be mean, could be proportion, could be variance, could be standard deviation, and so on like that. So because of that, I'm going to define parameter is a population characteristic value that we seek to determine. And let me tell you this, the only way to get parameter directly is to go to the population. Okay. Now, if I want to get parameter exactly, then I need to study everybody in the population. And you know what? We don't have that resources. We're limited by budget, and we want to take a decision on time. And that is the reason why we don't study everyone in the population. Okay, what do we normally do? We take a sample. Okay, we take a sample. Okay, so the sample is just like few, maybe out of millions. I'm actually going to choose like 500. I'm actually going to be fine with that. But the way I'm going to choose the 500, okay, I actually need to use a principle of randomization. I have to choose 500 from the population, giving equal chance to everyone in the population, so that I'm actually going to have the sample that was chosen will be a representative sample at the end of the day. That is when I choose the sample randomly. Now, whatever I calculate from sample is what we call statistic. But whatever we compute from population is what we call parameter. So because of that, I'm actually going to say Statistic is a numerical summary of the sample. Okay, statistic is a numerical summary of the sample, while parameter is a numerical summary of the population. Does that make sense to everyone now? Okay, now because of that clarification, I'm actually going to go into statistic now. Let me tell you this. I said whatever I compute from sample is what we call statistic. Now, statistically speaking, we normally, if parameter is theta, if parameter is denoted, if we denote parameter with theta, we're actually going to denote statistic with a theta cap. Okay, we denote statistic with a theta cap. Now, statistic is actually going to be unbiased estimator because, if I want to figure out if I want to get something from sample, I actually need to use an estimator. Estimator is a formula that we use, okay? Now, we're going to say it's unbiased, provided when I find the average of the statistic, if that average gives me the true value of a parameter, why are we finding the average of statistic? Because statistic varies. If I ask 1,000 researchers to go into a population and compute, let's say the statistic is average, you're actually going to have different value for average. And when you have different value for average, what we're going to do is to find the mean of your average, which is going to be average of averages. So if the average of averages give us the true value of a parameter that we're looking for, then we're going to say the estimator is unbiased. Otherwise, if it doesn't give us, that estimator is biased. And let me tell you this, what we want is unbiased, because you know what bias causes? Bias could cause underestimation or overestimation. We don't want that. Does that make sense to you now? Okay, that's what we mean. Now, I actually want to come here now. I remember in my last class, I show you, if the mean, if we are looking for population mean, which is a parameter, of course, before we can actually use sample mean to represent the population mean, then we are trying to say sample mean is an unbiased estimator of the population mean. So because of that, we can use sample mean instead of population mean. Okay. Well, I showed you that on Wednesday. Now, what of in a situation where we don't have a population variance, because we know it's going to be complicated or it's going to take a lot of time if I want to figure out population variance, because I'm actually going to need all the elements in the population. We don't have resources for that. And we end up just finding the sample variance. And how can I show the world that sample variance is an unbiased estimator for population variance? That is what I want to show you now. If you take a look at, give me 1 second. If you take a look at, let me see. Okay, so when you take a look at this guy, what do I want to do? I want to show that sample variance is an unbiased estimator of a population variance. Or what I try to tell the world, without population variance, can we actually use sample variance? This is a justification. What I want to prove now in statistics, this is a justification. Now, if I want to start, I need to first understand what is the formula for sample variance. Of course, we all know. Take a look at this guy. Right? That is the formula for sample variance, the one we divide by n-1, right? Now, if that is now what do we want to do? We want to take expectation of that, because when sample mean varies, sample variance also varies. So expectation of this, you know what that means? The mean of the variances. Maybe somebody get a variance, we get a variance, we got a lot of variance here, then we now find the average. That's what we mean. Now, if the average of the variances give us the population variance, then we can actually use sample variance to represent population variance. Now, we want to see now whether if that happened. Now, do you know that this guy here, if I open that guy, that's what I'm doing here. It's the same as that. Do you know what I've introduced? When I have summation xi minus x bar squared, do you know what I introduce in between? Okay, I'm actually going to show you what I introduce in between. So if I have summation x minus x bar squared, this is what I just did. Does that make sense? Because this guy will cancel that guy. That was why you see mu here and mu at the other side. Okay, that was just the manipulation that we did. Now, what is going to happen now? Okay, now you find ourselves here. If I use expectation to multiply all of that, okay, 1 over n minus 1 is a constant. It's actually going to come out. Then expectation, because I've already broken this guy into that guy, then expectation will chase the summation away. Okay, that's why you see summation, the expectation grab that. Is there any question on that? I need to take a look at that very well. There's any question? Okay, you can see that, right? Now, that was how we got that. Now, the next thing that I want to talk about, take a look at this guy. And this guy. This guy here. Expectation of a random variable minus mu all squared. That is the variance of x. Here, this is the variance of x bar. Look at here, x bar, x. So here, this is going to be sigma squared, because it's the same as variance. It's the same as variance of x. Okay, but you take a look at this guy. That will be sigma squared divided by n, because that guy is the variance of x bar. Is there any question? Okay, this is the variance of x, is sigma squared. Variance of x bar, sigma squared over n. Okay, now when that happen now, do you know that if I plug this guy here, because variance is constant, summation will turn to n. That will be n sigma squared. That was why you have this guy. Any question? And when I plug sigma square over n here, okay, it's going to be n sigma square over n. Can you now see how we got here now? See how we got here? Any question? Any question? You're good, right? I need you to pay attention. You're good, right? Now, what is left is just algebra. Okay? Now, if you take a look at this guy here, what is actually, that n can cancel that n. Take a look at this. So this cancel that, right? What is common here? Sigma squared. When you factorize it, it's going to be sigma squared into n minus 1, and n minus 1 will cancel this guy. Eventually, what do we have? Population variance. Now, this validates what we are doing in statistics. In statistics, we tell the world that instead of you to study everyone in the population, just focus on sample, because expected value of the sample of the statistic will give us the population parameter. In this case now, Statistic is sample variance. Expectation of it give us a population variance. Is there any question now? That's how to show that. Okay. Now, there's a question I'm going to move. Now, when we have an estimator is a method or a formula that we use in estimation. Okay. If I really want to know whether my estimator is going to do a great job, we got properties of an estimator. The number one property is what I showed you the other time, unbiasedness. An estimator must be unbiased. How am I going to know? Okay, I'm actually going to know when the expected value of an estimator equal to the true value of a parameter. Then what is the second property? The second property is the variance of a point estimator. Every estimator, we have a variance. Okay, and the variance will enable us to investigate how reliable, okay, how reliable is the estimator. Does that make sense? Now, imagine we have so many estimator, they are unbiased. Maybe this guy is an estimator, this is another estimator. Both of them are unbiased. But how am I going to know the best among them? The one with the smallest variance. Does that make sense? An estimator with the smallest variance. And that is what I'm trying to say here. If theta cap 1 and theta cap 2 are two unbiased estimators, because at times, for a given situation, we could have more than one estimator that we may suggest. I'm going to give you an example of that. If I want to find an average, okay, we have more than one estimator that can be used. What are the estimator? It can say that we use sample mean, sample median, or sample mode. Three of them are estimator. Does that make sense? So how do we know the one to use? If three of them are unbiased, why do we use mean? Why do we use mean? You know, it's sometimes. Why do we use mean? Because mean has the smallest variance. Okay, so that's what I mean. So the theta cap 1 and theta cap 2 are two unbiased estimator of the same population parameter. We want to choose the estimator whose sampling distribution has the smaller variance. Okay, that is, take a look at this guy. Situation where this happen, it means this estimator is better than that, because the variance of this estimator is smaller. The lower the variance, the more the efficiency. Does that make sense? Okay, now, and that was why I said, if we consider all possible unbiased estimators, there could be so many estimators that are unbiased. Okay, which one has the smallest variance? The one with the smallest variance is the most efficient. Does that make sense? Okay, now I want to walk you through how do we estimate the mean. Let me tell you this. What do we mean by estimation? Oh, estimation is involved whenever you are getting information from sample. Instead of us to study everybody, okay, we now focus on sample. Then whatever we're doing with the sample, we're estimating. And estimating is like approximating reality. Look at the word estimation. It's not exact. Okay? Now, let's say, so and in estimation, we got two types of estimation: point and interval. You know, point is when you get a single value. Oh, I get the mean, and maybe the mean is $60,000. That's a single value. A single value could be wrong or right. According to classical approach of probability, a single value could be wrong or right. And because of that, we consider interval estimates. Does that make sense? That's why when you see most of the articles in research, instead of us to just publish a point estimate, we consider interval estimate, because in the interval estimate, we actually are going to incorporate what I call the margin of error. The margin of error, it means I've considered error to the right, error to the left, and that was why you got this guy. Take a look at this guy now. Okay, if you take a look at this formula, the first, or I'm trying to say the true value of the parameter, that is the true values of the mean, lies between this and that. Do you know that this guy here, we normally use this formula. This guy here is a lower bound in the interval. This guy is the upper bound in the interval. And you know what? Statistically speaking, when you construct an interval, okay, there's all it is very sure that what we're looking for will lies in the interval. Does that make sense? Okay, now the lower bound, the upper bound. Now take a look at this. If you take a look at this guy, that is the margin of error. You know, the margin of error actually will enable us to see how sample reveal the overall view of the population. Without margin of error, there's no way we can actually rely on our estimate. I told you the other time, when I only got this guy, just X bar, that's a point estimate. It could be wrong. All right. Imagine we've committed a lot of resources to research only to be wrong at the end of the day. That's not good at all. Now, I need you to pay attention now. Do you know that the Z, I will check the value from the table. Now, apart from the Z, what is other one called? Oh my God, this guy here. That is the standard error. Standard error. Does that make sense? So which means margin of error equal standard error multiplied by multiplier, the Z multiplier. Okay, so we use the one that has Z in it, okay, when the see, when the variance is known, when the population variance is known, okay, and we have to be working with the normal population, and if the population is not normal, then the central limit theorem must apply. At times when the population is not normal, if the sample size at least 30, we're good. We can make use of that. Okay. Now, whenever we are constructing an interval, we normally associate that interval with the level of confidence, because we acknowledge the fact that when I'm defining something in an interval, there's going to be an error, right? Now we need a confidence, but we can never have 100% confidence. So we could have like 90%, 95, 99. Okay, confidence. Now, when I construct, because if I want to get Z, I have to specify my level of confidence. Because if I know my level of confidence, I will know what alpha is. If level of confidence is 95%, alpha will be 5%. You know, alpha is a level of statistical error. We also call it the level of statistical significance. So when the confidence level is 90, the level of statistical significance will be 10%. Does that make sense? Okay, now I'm going to walk you through. So when I say that I'm 90% confident, you know the meaning of 90% confident? The 90% confident means if I construct 100 intervals, the true value of parameter will only lies in the 90 of them. 95% confidence mean if I construct 100 intervals, the mean will only lie in the 95 of them. What are we trying to tell the world? We're trying to tell the world our model, our technique is not 100% efficient. I told you the other time, model that we're using in the world, in research world, even though we want to use it to depict reality, it will never give us an exact reality. That is an acknowledgement of the fact that there's always going to be an error. Does that make sense? Now I need you to pay attention to this now. You know, this is a meal, right? But take a look at this guy here. Can you see that guy? What happened to that guy? that guy, the lower bound is not, this guy doesn't fall within. So if there are 10 in number, and out of 10, and then the one, like this one now, okay, the mu doesn't fall in that one, then this represent 90% confidence. Does that make sense? We are 9 out of 10. That's what I mean. Now I want to walk you through an example now. I need you to pay attention. The average zinc concentration recovered from a sample of measurement taken in 36 different locations in a river is found to be 2.6 grams per millimeter. Find the 95% and 99% confidence interval for the mean. Okay, let me say this. The more the confidence, the wider the confidence interval becomes. Please take note. When the confidence level increases, okay, the width of the interval actually goes up, become wider. Okay, I just wanted to take note of that. Now, using that formula, you know what I just need to identify? This is the formula we want to use here. This is the formula. The only thing you need in this formula, what is your mean? What is your standard deviation? What is your sample size? What is the confidence level for you to be able to figure out your z-score? Okay, now I've already plugged that in here. Okay, we've already plugged that in. Okay, now for 95%, your z-score will be 1.96. We can check that from the table. How am I going to know? For 95%, what is going to be alpha? Alpha will be 5%, right? 5% means 0.05, right? Now, if you want to check your z-score, you know what you're going to do? You're going to do 0.05 divided by 2. That would be 0.025, right? Then you check that from the table for z, and that was going to give you 1.96. Okay, now when you take a look at, depending on the table you're checking from, the z value leaving on the 0.025 to the right and the 0.9. So by the time you check from the z table, that's going to be 1.96. And at the end of the day, what am I trying to say? Take a look at this. It is reasonable to say that the average lies between 2.47 and 2.73. This is more acceptable in the research world compared to when I just said the average is 2.6. That 2.6 is a point estimate. It could be wrong or right, even if we have done all the necessary things. It's 50-50. And that's why we don't want to trust, we don't want to risk that. And we needed to construct a confidence interval. So in most of that, so that's why you see that. Okay. Now, this is for 95%. If I want to interpret this guy now, I'm actually going to say we are 95% confident that the true values of the mean lie between this and that. But if you want to do 99, everything, oh, sorry, this will be 99 because take a look at this. This guy here, 1.96, by the time you solve that, that's for 95%. But for 99, the z-score is going to change to 2.5. You can see, now take note of something. For 95%, the z-score is 1.96. When I increase to 99, the z-score increase to that. Because the z-score increases, then the margin of error increases, then the wider the confidence interval becomes. Does that make sense? Okay. Now, any question on that? Any question? Okay. Now, what I want to walk you through now, let's say for instance, how do we decide on the sample? Maybe for instance, I actually want to figure out the average expenditure. The average expenditure, or let me just say the average expenditure per week by a student of this university. I want to actually conduct that study. How do I decide on the number of students that I'm actually going to choose randomly? We don't just choose a number. we need to be guided statistically. Now, this is what we call sample size determination. I want to decide on the number of number of students that I'm actually going to choose. Okay. If I want to decide, then I need to be able to disclose at what level of confidence that I want. Okay. And if I know the level of confidence, I'll be able to know the significance level. I'll be able to know my Z. Then I also need to disclose what is the population standard deviation that I can tolerate. Then E is margin of error. Within what margin of error? Okay. So if you want to go out and you want to conduct a survey, we don't just say, oh, I'm going to interview 50. No, we actually need to determine the sample size. And this is a formula that we're going to use to determine the sample size. So we need to be able to tell the world, because if you take a look at this, sample size and the margin of error, they are inversely related. The more sample that I take, right? The more sample that I take, the lower the error. You see, and that is the reason why the more sample we take, the more we are very close to the truth. Why are we not using the whole population in the first place? Because we're limited by budget. Does that make sense? Okay. Now, I need you to pay attention. Example, how large a sample is required if we want to be 95% confident that our estimate of mu, okay, in example 9.2 is off by less than 0.05. Okay, because they mentioned 95%. The z-score will be 1.96 all the time. 95%. Z-score is 1.96. Okay, and the 0.3 that you actually see right now is the standard deviation given, and the margin of error was 0.05. What are we trying to say? The sample size is this. So we normally round it up. Okay, this is going to be 139. Okay, we're going to say, therefore, we will be 95% confident that a random sample of size 139 will provide an estimate X bar different from that by amount less than 0.05. Do you know that if I increase my level of confidence, the sample size is not going to stay the same? Does that make sense? This is how we figure out the sample. We don't just choose sample arbitrarily. We need to be guided. Is there any question? Okay. But this is a sample size determination. If we want to estimate the mean, we have a different formula for sample size determination if what we want to figure out is proportion. This cannot be used for the proportion. This is focusing on the average. Okay. Now, when we're talking about confidence interval, confidence interval, you're actually going to see the lower bound, the upper bound. At times, we may not want to talk about the two sides of the aisle. We may only want to concentrate on just one-sided interval. Okay, when I say one-sided interval, okay, we have upper one-sided, we have a lower one-sided. Let me quickly take a look at this guy. Okay, you remember that the other time, this was the lower bound, this was the upper bound. Does that make sense? At times, we may just want to focus on one-sided, not two-sided. For the two-sided, we need two of them, right? Okay, so upper one-sided is the one where you are adding the margin of error. The lower one-sided is the one you are subtracting. Does that make sense? Okay, now I'm going to walk you through an example. Please, I need you to pay attention now. In a psychological testing experiment, 25 subjects are selected randomly, and their reaction time in seconds to a particular stimulus is measured. Past experience suggests that the variance in reaction time to this type of stimulus is 4 seconds squared. Past record. That should be a population variance. Okay, and that the distribution of reaction time is approximately normal. The average time for the subject is 6.2 seconds, give an upper 95% bound. Here is not asking you to two-sided. It's only trying to talk about upper. Does that make sense? That's a one-sided. Okay, now what am I gonna do? I'm just gonna use the one-sided one, the plus one. Just plug in. We're done. Any question? Okay, super cool, right? Do you know that this what we're doing lately with Dominate Final, right? I think I put it in the announcement today. 7, 9, and 10. That will make like 60% of the final questions. What we're doing lately. Okay, so just check the announcement section. Okay, now we are done with a situation where the population standard deviation is given, and the sample size is large. But what if in a situation whereby the population variance or population standard deviation is not given and the sample size is small? I remember on Wednesday I walked you to T distribution, right? Now, if we want to construct a confidence interval in a situation where the population standard deviation is unknown, okay, the population standard deviation is unknown and the sample size is very small, I think you know the threshold, right? When sample size is less than 30, that's going to be a small. Now, I quickly want to move because of my time. I'm going to move. Let me just show you the formula. Oh my God, this is the formula. Okay, what is the difference between this guy and the one I showed you before? The difference is that, yeah, the other one was a sigma. Sigma means population standard deviation, but this one is sample standard deviation. We use sample standard deviation when the population standard deviation is not given. Okay, and what do you see instead of Z? What do you see? T, right? You remember that Wednesday I walk you through T. I will check T from the table. If I want to check from table now, then I need degree of freedom for T. Now, this is a confidence interval when, you see, confidence interval of mu when sigma square is unknown. When sigma square is unknown and the sample size is very small. Because at time, when sigma square is unknown and the sample size is large, we can still use the other one, Z. Does that make sense? Okay, now let's walk through an example. Go ahead. Yeah, we're going to use standard deviation, sample standard deviation to replace the population. You know why we can do that? Because when the sample size is large, there's no meaningful difference between sample size and the population. Yeah. Okay. Now let's take a look at the example. The content of 7 similar containers of sulfuric acid are 9.8, 10.2, 10.4. How many of that? The data here is not up to 30. There's just 7 of them, right? That's a small sample. Okay. Now find a 95% confidence interval. We want to find that. What the only thing, and because they gave you data, which means they want you to find your standard deviation from the data. What you're gonna find is gonna be sample standard deviation. Now, this suffer to tragedy. Number one, the sample size is small. Number two, the population standard deviation is not given. Then I'm actually going to use the formula here. I'm actually going to use this guy. Okay. Now, when I start plugging in, of course, because the sample, I got 7. The degree of freedom is going to be 7 minus 1 because if I want to check T table, I need a degree of freedom. So take a look at that now. I've checked this guy from a table, from a T table. Okay. Under the degree of freedom 6 with, for 95%. Okay. I checked that under 0.05 level of significance. I got that. So at the end of the day, this is the mean. This is the interval where you are supposed, if you use the last sample interval here, you're actually going to be wrong. Okay, so this is small sample interval. Now I want to move right now. Okay, gotta move right now. Any question? Any question? You should be able to know the difference depending on the question. make sure you focus on your sample size and see whether you are giving sample standard deviation or not. Let me tell you this. When the sample size is large, how large is it large? At least story, even though the population standard deviation is not given, I can still use a large sample interval. I can still use z-score. Does that make sense? Okay. Now, the concept of a large sample confidence interval. So I said, often statisticians recommended that even when normality cannot be assumed, let me tell you this. We got two distributions. The population distribution, the distribution of the population we're choosing our data from, and the sampling distribution. Let me tell you this. When the population distribution is normal, okay? When the population distribution is normal, whatever sample size you choose, the sampling distribution will be normal. But when the population distribution is not normal, I'm going to say that again. When the population distribution is not normal, then automatically the sampling distribution will not be normal. But let me tell you this. There's something we can do. If the population distribution we're choosing from is not normal, how can we guarantee, how can we make the sampling distribution to be normal? Then the central limit theorem said, choose at least 30 sample size. Does that make sense? So if we choose at least 30 sample size, okay, then the sampling distribution will be approximately normal. And that will enable us to use a confidence interval that have a z-score. Does that make sense? Even though, what do you see here? We see a sample standard deviation, but we're going to be fine because the sample standard deviation it's going to be more or less the same as the population standard deviation when sample size is large. Now, the last thing I want to talk about today before I go is what we call prediction interval. You know, what we've been doing today is interval that has to do with the mean, right? What about interval that has to do with prediction? We make a prediction now. When you make a prediction, okay, we can have a point estimate of a prediction is dangerous. It could be right or not. Can we also have, as we have interval estimate for mean, can we also have interval estimate for prediction? So that we can actually say, okay, our prediction lies between that and that. Now, this is the formula that we're going to use. Take a look at the formula. Now, this is prediction interval of a future observation when variance is known. When population variance is known, this is the formula. You can say this is different from what we did the other time. This is not a confidence interval for mean, but this is a confidence interval for prediction. Okay, now let's see an example. Okay, due to the decrease in interest rate, wait a minute, due to decrease in interest rate, not in the United States. I think recently the Fed, I think they were increasing the interest rate, right? Okay, but this one is maybe we're talking about First Citizen Bank receive a lot of mortgage application. Of course, you know, if there's a decrease in interest rate, a lot of people will want to get money from bank. Okay, now a recent sample of 50 mortgage loans resulted in an average loan of 257,300, assuming a population standard deviation. Look at that. This is specified population standard deviation, okay, of $25,000 for the next customer who fills out a mortgage application. Prediction is forward looking. Does that make sense? Now we're going to talk about for the next customer. We don't know. The next customer is a random, you know, and it could be anybody. The bank want to have a picture like, okay, the next customer, you know, we really want to make a prediction of what is going to ask for. And we want that prediction to be on the interval. Take a look at that. Who fills out a mortgage application? Find a 95% of 95% confident prediction interval for the loan amount. Now, all what you're just going to do, take a look at this formula here. This is what you're going to use. Get the mean, the z-score based on the level of confidence, sigma, population standard deviation. Of course, inside the square root, n is the sample size. Now, when you do that, I need you to take a look at this. Oh my God, the next, you know, this is going to be good for the bank instead of just giving this guy. This guy is going to be a point estimate. That's not going to be fine because a single value could be wrong or right. And but when you describe it in an interval, okay, you actually, this is reflecting on reality. There's always going to be variability in reality. Okay, so the prediction interval provide a good estimate of the location of a future observation, which is quite different from the estimate of the sample mean value. Like for instance, if you compare this guy with when you do 95% confidence for the sample mean, is going to be different from this. That's what we mean. This is for the next customer we're predicting. And I told you, our prediction is forward looking. But when you are just talking about mean, if you're only focusing on average, then that is backward looking. Backward looking in the sense that you're actually going to do that in the group level. Okay. Estimation of average is based on the group level, but when it comes to prediction, it is based on individual level. Does that make sense? Okay. That is all. We're done. Any question today? We're done. Is there any question? Before the end of the week, I think I put that in the announcement. I'm going to put final practice question. I need it. We focus more on chapter 7, 9, and 10. This is 9, right? I this 60% of the final we focus on that, and of course chapter 2, 3, 4, 5, and 6. 2, 3, 4, 5, and 6 we only contribute 40% to the final. But you know what? You're actually going to see the pattern of the final in the practice question. That's what I always do. Okay. Is there any question before I go today? Go ahead. Do we do chapter 8 in this class? Does anybody have idea? Do we do chapter 8 is about what? Okay, I'm going to check. Because that was a chapter we skip that we didn't do. And I want to be sure. I know chapter 7 is okay, chapter 8 is sampling distribution. I think 7. I'm actually going to check. When I check, I'll check my if I found something, then I can edit. Chapter 8 is sampling distribution. It's not going to be part of the final. Okay? I think I just remember now. Chapter 7 is function of random variable. Of course, you have to practice a lot on Jacobian. That will definitely be part of the final. I think chapter 2 is just probability, where with Bayes theorem, stuff like that will be part of the final. Chapter 3, I remember we did a network. Bayesian net, of course, that will be part of the final. Chapter 4 is mathematical expectation. That will be part of the final. But you know what? The weights in the final, 60%, we focus more on 7, 9, and 10. 60%. Why 40% we spread across 2, 3, 4, 5, 6, 7. I'm sorry, 6. 2 to 6. No 8. Okay? Make sure you all stay safe and have a lovely weekend. Bye for now, everyone.